In this video, we're going to differentiate and integrate power series. If the function given by this power series is equal to the expansion here, if that power series has a radius of convergence where r is greater than 0, okay, on this interval, and f is differentiable and therefore continuous, then we can find derivatives and antiderivatives. So we're going to look at the effects on the nth term when we differentiate and the effects on the nth term when we integrate. All right, let's make an addition back up here in your notes. As you guys can see, if you were to generate these terms right here based on this power series, you would get this expansion. Okay, let's go ahead and add a subscript here. Let's add a 0 down here. See if I can. All right, so that should be a sub 0 when n is equal to 0. Just a little typo there. All right, let's come down here and look at number 1. Okay, if we want to find the derivative of this power series, we can go through and term by term for each of these terms, we can differentiate. This is a power function, we're going to use the power rule. Okay, so the derivative of a constant, it's going to be a constant value 0, so we're going to focus our attention starting right here. Okay, think of that as an exponent of 1. Okay. So the derivative of that first term is going to be using the power rule and the chain rule, a sub 1. Plus, let's move on to the next term. Using the chain rule, we're going to have twice the coefficient a sub 2 times quantity x minus c to the first. And of course, we're going to multiply by the derivative of the inside function, which that's just going to produce 1, so we can move on. All right, continuing in this fashion, finding derivatives. So term by term, we can find each of the derivatives of the term since they're power functions. And we'll do one more just based on the observations that we see here, even though we don't have that term up there. What if we had a 4th degree power? So looking at the patterns here, we see that the exponent is 1 less than this value and that subscript right there. Plus, dot, 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 plus, let's get a representation for the nth term. Okay, well here's the nth term right here. So finding the derivative of that nth term using the power rule would have n times a sub n quantity x minus c raised to the n minus 1 power. So with the power series, we can differentiate it term by term, or we can differentiate the expression for the nth term. What if we wanted to take all of this and collapse it into summation notation, a nice convenient form that represents all these terms? Okay, I'm going to leave this n value off for just a second. We'll talk about that here when we're done collapsing this. Well, collapsing it, we've already found the nth term, so let's just dump it in right here. As you guys can see through the process of differentiation, we lost this constant term right here. So we lost a term. So if we wanted to express all of these terms right here, we wouldn't start with 0, we would start with 1, since we lost a term. Okay? And you can just check to make sure that when you index it starting with 1, that when you plug 1 in for n, it does generate just a sub 1 here, and then all the the following terms. Okay, so differentiating a power series is differentiate term by term, or just differentiate the nth term, paying attention to that little detail here of the index of summation, that when we lose a term, when you differentiate, we're just going to start off this expression right here with a 1 to represent all of these terms correctly. Okay, let's look at the notation for integration too. All right, so when we look at the integral of f of x, and here is f of x up here, it's our function that's defined by this power series. If we're going to integrate that, we can take each of these terms right here and find an antiderivative using the reverse power rule. I think I'm going to start this off, though, the integration with the constant of integration. I know in past common practice was to add the constant of integration, the c, at the end, but we're going to start off the power series with the c so that we don't forget it. All right, so we're going to have c plus Looking up here at these individual terms, let's start with a sub 0. Okay, I can rewrite that as a sub 0. I'm going to come down here and write it just so we have a visual. A sub 0 times quantity x minus c raised to the 0. Okay, if we're going to integrate that term right there, okay, reverse power rule, increase the exponent to 1, divide by the new exponent of 1, so that term will be a sub 0, quantity x minus c to the first, divided by 1. Moving on, plus, okay, I don't need to rewrite this because the visual's there. I'm going to increase the exponent to 2 and divide by the new exponent. So that's going to be a sub 1 quantity x minus c squared divided by 2. And we'll continue with a few more terms. So antiderivative here, a sub 2 came from the second term up here, or the quadratic factor. The exponent's 1 more than the subscript divided by 3. And we'll do one more. And then we have the plus dot dot dot. Let's get a representation for the antiderivative for the nth term. So that would look like a sub n quantity x minus c raised to the n plus 1 over n plus 1. Plus, and indicating it continues. And that's why I thought it would be good to put the constant of integration at the beginning. All right, let's take and do like we did up here and collapse it into summation notation. Okay. And I'm going to leave this index off here for just a second. Okay, so collapsing all of that just requires us dumping the nth term down in here. And I needed to put the c first. C plus, I should put c plus here. Okay, and then the expression that represents all of these later terms right here. So c plus this summation notation. Okay, let's go back and look at what we should start n with. Through the process of integration, we could introduce an additional term that wasn't part of the previous the original power series. So it's not like we're losing a term like when you differentiate. So if you're introducing or possibly creating an extra term, think about that when you're trying to figure out what to start n with. Okay? Or you can just simply look up here and say, well, what's the required n value here that produces this first term? Well, if you start with 1, think about when you put 1 in here, you're going to jump immediately over to this term. So we need an expression that also accurately represents this term right here. So that would have to be 0. Okay, so a sub 0, testing it, a sub 0, 0 is here, that's a power of 1, 0 is here for this n, division by 1, so it all works. So just kind of pay attention to the index and what you should start with, and a real good check is just to see, make a guess if you need to, plug it in and see if it produces the first term and all subsequent terms. So for functions that can be represented by power series, okay, we can integrate, we can differentiate, as long as we're doing that on the radius of convergence, the interval of convergence. Okay. So one note real quick here. So when you do differentiate or integrate, the radius of convergence is going to be the same for the differentiation and the integration. However, the interval of convergence, the endpoints may change. So we're going to have to do some additional tests. If we differentiate or integrate power series, we're going to have to do some additional testing on the endpoints of the interval of convergence if we have endpoints to see if the interval of convergence matches the function's interval of convergence. So that's kind of where we're going towards. Okay, we'll do that on the back of this paper, but let's finish the bottom down here. All right, you might want to take the time to read these 2 paragraphs. It's a recording of what I just mentioned about the interval of convergence when you integrate or differentiate a power series. Okay, let's look down here for some extra practice of what we just did. All right, let's find the derivative of this function defined by this power series that's been expanded in this format. So I'm going to go ahead and differentiate term by term. Okay. It's kind of a unique example we're going to see here in a second. The derivative of 1, of course, is 0. Derivative of x is 1. Moving on to this term, power rule. Remember, this is just a constant multiplier, 1 over 2 factorial. So bring the 2 in front. It's going to cancel with the 2 down here. And so I'm just going to get x. Okay. Finding this derivative, you're going to bring the 3 in front, x squared over 3 factorial. We'll do the cleanup in a minute. Derivative of the next term, and then we can find the derivative here. Okay, a little cleanup underneath it. Okay, I can see that I can cancel this 3 with this 3, leaving 2 factorial in the denominator. I'm going to be able to cancel this 4 with this 4, leaving 3 factorial in the denominator. Okay. Even though the next term isn't here to clean up, well, let's think about what that's going to look like based on the pattern we're seeing so far. Well, that would be x to the 4th over 4 factorial, and that would continue, plus dot dot dot. Let's clean this up right here. N would cancel with the n down here, leaving n minus 1 factorial in the denominator, with x raised to the n minus 1. Okay, but thinking about this right here, okay, if we think about this term right here, if you think about an expression that represents the next term after that, and maybe I should squeeze it in right here, okay, let's think about the next term that would follow before I actually would do dot dot dot, because it's kind of interesting to look at. Okay, plus I'm going to change this right here. Okay, well the next term would be what I'd get when I would increase n by 1. So that would add 1 here. It would add 1 here. So that next term that follows would just simply be x to the n over n factorial. Now I'm going to do a plus dot dot dot. Well, you probably already see the behavior of the derivative is exactly this power series right here. Well, what function have we studied in the past where when we have a function, its derivative is equal to it? All right, so I'll leave you with that thought momentarily. Let's come back over here. So what is the derivative? Well, the derivative is actually just itself. So notice the index right here starts with 0, and you can check if I use 0 and plug 0 in for n, I'm going to get x to the 0 over 0 factorial, which that's just going to produce the 1, so that's fine. Would it have been okay to start with or use this nth term expression? It sure would have been. So let's see what that looks like. I'll leave this starting place blank for just a moment. Okay, what if we would have used the representation for this nth term instead? Okay, well think about what you need to generate. You need to generate a 1 here. So can I start at 0? No. I need to start at and make an adjustment and start that at 1. Okay. So that's just one of those little details you kind of have to pay attention to, but always just do a verification with your expression and your index with the first or and subsequent terms if you want to. Okay, thinking about how this is kind of special and, a further look at differentiating power series, think about why this is special. The derivative here is exactly the function, okay? And the function you might well remember is f of x is equal to e to the x. Because the natural exponential's derivative is itself. There's just kind of an interesting case. So notice that this was true. Do you recognize this function? Yes, and it is this exponential function. Okay, we're going to look at the back in a different video.